Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, as always, Ricardo Lopes, and today we're joined by Dr. Leo Tiokhin. He is research fellow at the Institute for Advanced Study at the University of Amsterdam, an interdisciplinary research specialist at the Center for Unusual Collaborations, and a postdoctoral researcher at the Eindhoven University of Technology. Dr. Tiokhin is a meta-scientist who studies the forces that shape how scientists do their work and make inferences from the populations that they study. Much of his research focuses on how incentive structures affect scientific efficiency and reliability, and how we can improve the recognition and reward structures in science, and those are the topics we're going to talk about today. So, Dr. Tiokhin, welcome to the show. It's a pleasure to have you on.
Hey Ricardo, it's a pleasure to be here.
Great. So, okay, my first question would be then, since you're studying, or one of the things that you study is science as a sort of social phenomenon and an object of study of the social sciences, what can we learn about what it is and how it works with that approach?
So one way you can view science is like you might view any other culture, right? So every culture has its own norms, its own rules by which people um, are expected to behave, its own things that are considered deviant, its own actions that are rewarded, etc. So science is just, a unique um, institution that has people and is characterized by its own norms, rules, and these people want to achieve certain things within that institution by playing by those rules, by getting rewarded for certain types of research, um, by being punished for certain types of deviant actions, etc. So the answer to that question would be the same thing as why you might want to, as an anthropologist, go and spend a lot of time trying to understand uh, the people that you're studying anywhere in the world. For the same reasons, you need to spend quite a bit of time with scientists to understand what it is they value, why it is that they judge some research as better than others, why they pursue certain research questions than other ones. So, yeah.
Yeah. And I mean, in the introduction, I mentioned you also study incentive structures, or that's at least one aspect of how the the culture of science works, let's say. So, in that way, when it comes to its incentive structures, is science an institution different from all others, or not?
Yeah, that's a good question. So I don't I don't view it as entirely unique. It has some sorts of incentives that overlap with incentives we see in other areas of life. So, for example, despite the fact that science is not supposed to be very conformist, you're always supposed to be open to criticism. Criticism is supposed to be easy to publish. There's always supposed to be debates. I think it is more so like that than many other institutions, but there's also a lot of conformism within science. So within any given field, you're expected to use certain particular methods. Maybe in psychology, you do statistical analyses with ANOVAs, or are used to certain experimental designs, or whatever field you're in, it has these own norms. And so if you deviate from those and all of a sudden you introduce a new analytical technique, even if it's better, people aren't used to it and they don't know what to do with it. And oftentimes there's a bias against novel introductions, even if eventually maybe it becomes something that people recognize is an improvement. In the beginning, there's people who try and introduce novelties, oftentimes face challenges, and that's the same in any culture. We know humans are quite conformist, and so conformist transmission is a big factor that is one of the things that maintains cultural differences between groups, and that's the same reasons we see in science. We see a lot of sort of differences in methods between fields just because that field happened to have had that method at some point and it became the norm. So that type of thing is very similar to what we see in any other culture. On the other hand, science does have some unique characteristics that have arguably helped it to be quite successful and be a successful institution for getting us towards a better understanding of the world. So one of those things is the ethos of organized skepticism. It's one of the norms of science identified by sociologist of science Robert Merton, who wrote about this in the middle of the 20th century. And it's the idea that claims are not supposed to be just accepted because some famous person said them or whatever reasons, other reasons just at face value, but claims need to be and exceptionally scrutinized. And in fact, scrutiny by the scientific community is one of the mechanisms by which you differentiate claims that are stronger from those that are weaker. And this sort of skepticism is something that any scientist knows. Many fields have this culture of just criticism and skepticism and things like this. Again, this is in theory. This varies a lot between fields. So, and if I go and give a talk to economists, I'll probably leave crying because of how much criticism I'm going to get. Whereas when I give talks with psychologists, it's generally quite friendly. And we also know criticisms are oftentimes really hard to publish. If you find errors, journals don't want to publish that. So in practice, it doesn't always work. But in theory, that's one thing that helps science to be as effective as it's been.
Mm-hmm. And when it comes to these different incentives that play a role in science, which of them have a positive impact on the production of scientific knowledge?
That is a very hard question. Yeah, it's hard because we don't have a good way of, I'd say, there's no agreed upon way of operationalizing what is good for scientific knowledge accumulation. So how would you go and decide if something is improving knowledge generation? Well, you have to operationalize it in some way in practice. And so maybe you can look at some specific problem. So you're trying to increase yield of a crop or something like this. And so you can see, okay, how has crop yield increased in the places where they've had one incentive or another? So, but you focus it in on this narrow sort of operationalization, or maybe you can see, okay, there are some well-known problems in a field, and so at what rate are we solving those problems or something like this? So I think there are some types of things that I have suspicions are good for science, even though we don't have a good definition of exactly what it means for something to be good for science. So, for example, more openness of data sharing than we have now in science, where we have full-on secrecy. Open transmission of information tends to be good for group functioning. On the other hand, it also means that if something's wrong, it can very quickly spread. So that's why modularity in systems is good, because it can keep, if one thing breaks down somewhere, then not everything breaks down. So again, it gets really, really complicated. But there are some things I suspect are good for science, but I think this is a big ongoing question, and people are seriously thinking about, okay, if we want to answer this question, how do we go about understanding what it even means to get something like knowledge accumulation, or what it means to talk about something being good for science?
Mm-hmm. And would your answer be the same if I ask you what are the kinds of incentives that harm science?
So the interesting thing is, intuitively, so you would think it should be the same, right? So if I can't answer the first one, then why would I be able to answer the second one? But on the other hand, it does seem like that I can identify quite a few behaviors that I don't see any way in which having more of them would be good or something. So for example, like scientific fraud, where you're just completely making up some data or whatever. Data is usually the way it works, but I don't see any way in which that could possibly benefit knowledge generation. Maybe I'm not creative enough. Or, for example, many questionable research practices where, so this is a big problem in many fields where scientists engage in things that are sort of, it's not clear if they're good or bad in all conditions, but oftentimes, for example, if you conduct many different analyses and then only report the ones that worked, which is something that, people do all the time, then to other people, it looks like you only did this one analysis that you said you did from the beginning, but really you just tried out a bunch of things and then only reported you sort of cherry picked the ones that worked. And so other people, what this does is it increases the chances that the thing you're reporting is a false positive if you're reporting only the thing that worked, and other people don't know that. So these types of things, I think, are generally bad, despite the fact that we don't have a good definition for what is good.
Mm-hmm. So I would like to ask you now about two different concepts. First of all, what is scientific efficiency?
So efficiency, the general concept of efficiency is accomplishing some goal, doing some task in a way with the minimum investment of effort possible, right? So you can think about anything, any task we might do in any domain in this way, including science. So if I want to get my research out to the public or to other scientists, maybe the most efficient way would be I write it up and I quickly post it as a preprint or something like this. Maybe it doesn't require that much effort. The information is there and I don't have to go through some sort of lengthy process of maybe formatting it for a specific journal, waiting a long time for it to get published. So that waiting and the extra time we spend in the publication system, this can be viewed as a form of inefficiency. So anything that allows us to do the same thing, to achieve the same goal we want to achieve, with less time, with less money, with less effort, those are things that improve scientific efficiency.
Mm-hmm. What about scientific reliability?
So reliability, the way it's often talked about, is about whether you can consistently do something. So for example, consistently get a certain finding. So if I am doing an experiment to find a certain effect, and every single time I do an experiment with a certain method, I reliably get that effect. That is, it's something that emerges consistently. That's what we think of reliability. We also talk about reliability sort of sometimes casually synonymously with trustworthiness, because if we talk about a finding being unreliable, it means, sometimes people can find it, sometimes they can't find it. They don't exactly know what conditions it's the case that you can find it in or not. And so people don't know if it's trustworthy or not, of course, unless then you figure out the conditions in which you can find that effect. So I'm interested in increasing reliability because what we've learned in the last decade is that many scientific findings are not reliable, in the sense that many of the findings that we see in the published literature, when other people try and follow the same procedure, if it was reliable, they would be able to find the same effect, but they can't find the same effects. And this is the case in many fields, so ranging from cancer biology to psychology to philosophy, to economics. So if we want to be able to trust the scientific literature, it's nice if that literature is reliable.
Mm-hmm. So with that in mind, and things like the replication crisis, for example, are there reforms that can improve scientific reliability?
Yeah, so if you're focused just narrowly on reliability, there have been some reforms that have been proposed within the last decade that we have reasonable reasons to believe will improve reliability. So for example, a simple one would be running studies with higher statistical power. So statistical power is the ability of your study to detect a positive effect or a true effect when that effect is there. So if you run a study with not that many participants, which was the norm, for example, in psychology. Apparently, there was just these heuristics that you were supposed to run like 20 participants per cell in your 2x2 design for whatever reason, I don't know. And then maybe it got bumped up to 25. So these kind of arbitrary rules, oftentimes you would have very low statistical power. You would have statistical power of like 20% or 30%. So that means even if there's an effect, you're only going to find that effect, 2 out of 10 times or 3 out of 10 times. And so you can't reliably detect that effect. So one easy way to improve reliability is to just increase your statistical power. So actually run studies that actually have enough of a sample size to be able to find the effect that you're looking for. And there's other ways, and many of the ways that increase reliability also are just other ways of reducing noise. So you're basically reducing noise when you're increasing sample size. So you can improve your measurement methods, right? You can get a tool that really precisely measures what you want, so that it's not the case that sometimes you get one finding, sometimes another, and you don't understand why, and it's because your measurement tool isn't actually measuring the thing reliably.
So when it comes to academic publishing, could you explain in what ways do information asymmetries and conflicts of interest incentivize scientists to deceive journals about the quality of their research?
Okay, so we're moving to deception, from reliability to deception.
Yeah.
Nice. So this question, I guess, is referring to the honest signaling paper that I published last year.
Yes.
Yeah. So, to be able to sort of understand this question about deception and what that means in academic publishing, we were coming at this problem. So first of all, it's, we need to know what we mean by deception. So we were coming at this problem in the way that sort of biologists might think of deceptive signals. So when we think of in the animal kingdom, organisms transmit information in many ways, and one of the ways that they transmit information is they give signals. They do something. A peacock might show its tail or something like this, or a gazelle might leap up in the air and do the starting thing, or other birds might do dances to try and lure a female into mating with them. So there's all these things that animals do to transmit information, and a central question in theories of signaling is why is it that they're ever believed, in the sense, like, why, if they could potentially lie. So let's say I'm a peacock and I'm trying to transmit information about how great of a mate I'm going to be, why don't I just say I'm going to be a great mate, even if I'm a crappy mate? And so in that context, there's some true state of the world. So I'm a peacock and I'm either in good quality or bad quality. And if I give a signal that's honest, that's telling another peacock, a peahen, I guess, what my true quality is. So I'm a crappy peacock and I say I'm a crappy peacock. So that's honest. But if I say I'm a great peacock, the best one in the world, you should definitely mate with me, when I'm a crappy peacock, then that's a deceptive signal. So deceptive signal is something it's a signal that's not corresponding to the true way you actually are. And this fits with how we talk about this. We can talk about this. I mean, in humans, sometimes people think about this having to do with your motivations. You intended to do something, but we don't think about any of that. We just think about, if I tell you one thing, but actually the truth is something else, that's deception. Mm-hmm. So anyway, and then this is going to be a bit of I don't want to go off too long on this, but one of the problems we were interested in is the problem of this kind of deception in academic publishing. So basically, the gist of the problem is that scientists have a lot of incentives to get their work published in certain journals, like high-impact journals, Nature, Science, Proceedings of the National Academy of Sciences, whatever. Every field has their specific journals, and scientists get grants based on the journals that they publish in, promotions, they get prestige. So there are big incentives to be able to publish in these journals. And so scientists have this incentive to sort of do whatever it takes in order to get their work published in those journals. And the thing is that when you ask about information asymmetries, the thing that refers to is that one party has more information than does another party. So in this case, when scientists submit their paper to a journal, yeah, they write up their research. They don't write up everything. They maybe did 10 experiments, 2 of them work, they write it up. I'm not saying this always works like this, but there are certainly there's a possibility for this. Or you do data analysis and you try it out in many different ways and you only report some of them. So you know everything about how you did the research, but all that the journal sees is the paper. So there's this asymmetry. And so that asymmetry and the fact that there's an incentive for you to sort of make the journal think your paper is as good as possible creates this possibility for deception, just like it does in the animal kingdom for deception about your own quality. We are interested in, okay, what are these conditions where scientists have these incentives to deceive journals about the quality of their own work?
Mm-hmm. So are there any mechanisms that can ensure honesty in academic publishing?
Yeah, so this is the exact focus of our paper, actually. So what we do is we take some of these insights of these mechanisms from biology and actually economics, because these things were discovered, some of these were discovered around the same time in the 70s in both discipline, and we apply them to the publishing system. So one interesting one, I think, that economists have known about for a while, but that wasn't quite known in the meta-science community, is the role of actually inefficiencies. So you asked earlier about scientific efficiency. It turns out that actually, so the publishing process is inefficient in many ways, and people are annoyed about these inefficiencies. It takes a long time to get your paper published. You have to format your paper in stupid ways. All of these things, you have to pay money. But it actually turns out in our model, what we find is that these inefficiencies actually serve a function, and the function is that they prevent people from trying to submit low quality papers to high ranking journals. And the reason they do it is you can understand this intuitively a bit. That you can think about, if you have a bad paper that is probably going to get rejected, but maybe it's worth, I'll just try it out. I'll submit it to Nature and see, maybe it will slip through peer review. If there's no cost to doing so, if there's no monetary cost, and if there's no time cost, if you just get a response within 2 days, then why wouldn't you do it? And a lot of people do this. They just try out a bunch of journals until it gets accepted somewhere. But if every time you have to do this, there's a 6-month delay, or you have to do annoying formatting, or you have to pay $5,000, you're really going to think carefully about, do I want to pay this cost to submit my crappy paper to this higher ranking journal? If your paper is good enough, you'll probably still do it because you think it has a good enough chance of getting in. But if your paper is bad, then these inefficiencies, they create this set of conditions where it's only worth it to submit some papers to those journals and not others. And that's one of the insights, and this comes exactly also a similar insight from signaling theory in biology and economics.
Mm-hmm. Still in the realm of scientific reliability, are replications always worthwhile?
So, do you mean, maybe you could elaborate a bit on what you mean by that question?
Yeah, if it's always worthwhile to try to replicate effects, studies, or
Yeah.
if there's a certain point from which, it's no longer worthwhile to do so.
Yeah. Okay. Yeah, so the easy answer is no. Replications are not always worthwhile, so nothing is
Yeah.
always worthwhile. Usually there are always some sets of conditions you can find that something's not worthwhile. So one easy condition in which something's not worth to replicate is if a bunch of other people have already replicated it and you're really, really confident in a finding. So if you think about when replications are really worth it, well, one general framework you can think about is how much information do I gain by doing this replication? So how much information do I gain, or how valuable is that information? And so if it's the case that 20 other people have replicated something, like in psychology, the Stroop effect or something like this, then there's really little value to doing it again. You already are so confident that this is a finding that you don't need to replicate it. It also might not be worth replicating something in other conditions. There are, for example, maybe you will learn a lot, but nobody cares about a certain finding, and it's really going to be costly for us to replicate. It's not theoretically important, so that might not be worth replicating. So actually, it's actually this a really big question now that people in meta-science are thinking seriously about, because basically pre-replication crisis 10 years ago, replications were really hard to publish in many fields. So now we've had this sort of good change in how science works in some fields, where now there's some funding to do replication studies. There's some journals that will specifically publish replication study formats, so it's sort of great. But now we don't know, okay, which studies should you replicate? You know, how much should we invest in replication? So these are becoming the big questions now. And there are different frameworks and suggestions to try and understand that. And they typically focus around how much information do you gain, and is it actually valuable for us to replicate the study, or is it kind of a waste of time because nobody cares?
So within science, are the social sciences particularly problematic?
So if you mean, I'm not sure. It depends on, I guess, what you mean by problematic and in which types of parameters or domains, you know?
Probably I'm referring more to scientific reliability and replicability and things
Right,
like that.
right. I want to say a cautious yes for two reasons. The one is that the phenomenon that social scientists study are maybe not less deterministic, but maybe more chaotic than some of the phenomenon that, for example, physicists study, right? So because of this, maybe small differences in initial conditions and how you measure something can have very big later effects on the outcome. So it can be really hard to even know why, to get a reliable effect, basically. Humans have all sorts of weird stuff that affects their behavior, and depending on what scale you're looking at things at. And so the problems we study are they're more complicated than some problems that other fields study. And because of that, it just becomes really hard to get reliable knowledge. Of course, it depends on the scale. Sometimes, for example, you might be able to know the distribution of some behavior if you do an intervention, or the distribution of outcomes, but you might not be able to predict the specific outcome. And there was another reason that I thought the social sciences might be problematic. And I think that's just more of an inductively, it seems like in many of the fields in social sciences, we're just making slower progress than we'd like. So sometimes I feel like I'm not really sure what we're learning. If I were to come back 10 years from now or something like this, and I were to try and catch up to the latest theory in much of psychology or in much of anthropology, would much have changed really? Would it maybe take me, sometimes I suspect it would take me like 2 weeks, and then I would catch up to the latest theory. So whereas if I wanted to, so that's telling you something about the rate of progress. Yeah, and even if you don't look at it that way, if you just look at what does it seem like we know about the world from disciplines like physics versus disciplines like psychology, it seems like we've been able to learn a lot more. So something Of course, people might say we've been studying physics for a longer time, but I don't think that's the only explanation. So there's certainly something about the social sciences that makes it that progress is harder.
So, and I mean, my next question is about the topic that I probably explore the most on my channel. I mean, all things related to evolutionary theory and evolutionary approaches to human psychology and behavior. Do you think that these kind of approaches can help the social sciences?
If I just say yes, do we move on to the next question? Then I'm kidding. No. So no, I actually was trained in the evolutionary social sciences. I worked as an undergrad at UCLA at the Center for Behavior, Evolution, and Culture, and then my PhD was in evolutionary anthropology at Arizona State University School of Human Evolution and Social Change with some people that you've interviewed on this podcast, like Rob Boyd and
Yep.
Clark. Actually, I think you had an interview with Clark as well, who was at UCLA. Still is
Clark
Barrett.
Barrett.
Yeah,
Yep.
yeah.
Yes.
So of course, part of me is very passionate about the evolutionary social sciences, the potential for evolutionary theory to help serve as an integrative framework for the social sciences to help us ask better questions. So, in some sense, it's impossible to say no to that question because humans are the product of evolution by natural means of natural selection. So every aspect of human, yeah, human cognition, human behavior, even societies which have been subject to cultural evolutionary processes, everything is a result of some sort of evolutionary process. And so, of course, evolutionary theory be needs to be an overarching framework that helps people to think about human behavior. So that's not really, for me, that's not really a question up for debate. Now, I do think that, I don't think the current frameworks that we have in evolutionary social sciences, which if I roughly divide it up, I don't know if I'm outdated now, but in terms of behavioral ecology, evolutionary psychology, and gene cultural coevolution, if you had just those frameworks and you were trying to understand humans, I think you would really fall short. So there are many other, things about human societies that those frameworks don't point your attention to. There are many things that other disciplines know that the evolutionary social sciences sort of ignore that are maybe consistent with evolutionary theory, but they're not explicitly derived from some sort of adaptationist framework or something. So I'd say I'm not as dogmatic about how much the evolutionary theory needs to be the one thing that we all sort of use to ask our questions. I think pluralism is important in science, but at the end of the day, everything needs to at least be consistent with what we know about how evolutionary theory shapes the design of organisms.
So I guess that a somewhat big issue in the social sciences has to do with cross-cultural research and the protocols that people apply across different cultures. And I mean, two examples that come to mind is the weird problem and also the work that's been done by Clark Barrett and others in the Geography of Thought project. I mean, how careful should scientists be about when they're going about applying protocols that have been honed on a particular subset of humanity?
Yeah, that's a funny question. So I can just easily say very careful, and then again we can move on, I guess. Do you have a specific thing in mind, or should I just give my general thoughts on the question?
Well, I mean, just the general thoughts because of the issues we know nowadays about how the variability of human psychology, for example, across different
Yeah.
cultures and things like, as you mentioned before, gene culture coevolution. I mean, to what extent when we're studying or when we hone a particular protocol in, let's say, this is perhaps the most common in weird societies, how careful should social scientists be about applying it in other cultural contexts?
Yeah, so this isn't something I've worked on in a while, but generally when you're doing research, you're making a bunch of assumptions. So when you develop a certain method, you make assumptions about the way participants are going to interact with that method. They're going to interpret the questions, maybe the way that you intend them to interpret it, that their responses mean what you even think they mean. Well, there's all these implicit assumptions. They can even be referred to as sort of auxiliary. You have these auxiliary theories that sometimes philosophers of science discuss, in the sense that whenever you're testing a theory, you're testing both the substantive theory and all these other assumptions that the experiment's going to work the way you intend, and the participants are going to respond the way you intend, and there's not going to be a ghost that interferes that you don't know about or whatever. So in this sense, the thing is, when we come up with many of these protocols, we are doing so and we're testing them usually on, I mean, it doesn't matter whether we call it weird or whatever, but you're testing them on, let's say, college undergraduates, which just happens to be the most common population people study.
Right.
You test them on college undergrads, and then the undergrads sort of respond in the way you think. They tell you they understand the task. Maybe you spend decades refining some protocol, like a Likert scale or something like this, and they seem to, when they're more angry, they pick the bigger number, and when they're less angry, they pick the smaller number, and then you're happy that it measures it. But so then you kind of forget about these assumptions because, or maybe you didn't think about them in the first place, and you had the same assumptions in your folk model of how people will respond as do your participants because you're from the same culture. And so when you go to different cultures and people have different norms, they interpret things in different ways. They maybe interpret status interactions in different ways. They see you as an external researcher, and maybe they feel like they need to act a certain way towards you. Then if you just take that same task and you just give it to them and assume they're going to interpret it in the way you intend, that's a huge assumption. Maybe they will. Maybe you've come up with a magical cross-culturally invariant task. But if you don't, then you don't know what your data mean. And this is a big risk of that people who have spent their lives doing cross-cultural research. So you mentioned Clark. You had Joe Henrich on here. All of these, any anthropologist who's intensively done field work knows this much better than I do. I've spent a few seasons in the field running some studies and designing studies, but you can really get misleading data. So in that paper, maybe just one example, Dan Harushka and myself and co-authors had this paper about learning from failures of protocol in cross-cultural research. And in that paper, there's this nice example of what happens when you take a basic intelligence test, for example, that's honed using like 2D objects on paper where participants have to, there's like square, triangle, whatever, and then you have to fill in what a certain missing piece is. And you think that that's cross-culturally invariant because, yeah, they're just these symbols and people should be able to interpret these symbols and whatever, there's no language associated with them. But there's a nice study where when people take this task and then they give it to school children in Zambia, the school children perform really badly in a way that seems, and it's a hugely right-skewed distribution where most of them are getting very low scores on this. And if you didn't question the assumptions of the test, you would come to the conclusion that, maybe these children are not that smart or something like this, right? Which, sure, there might be. Anyway, so that could be one idea. But what they did in the study then is they took the same task with the same logical structure and everything, and they just changed the materials. Instead of having 2D objects and these logically abstract tasks of these objects that children were used to playing with, they used 3D objects like beads and sticks, things like this, that the children were used to playing with. But they kept the task, everything about the logical structure of the task was the same. And when you do that, then you get this nice normal distribution of scores of performance on this, and you have children performing way, way, way better than they did before, even though the task, the structure is exactly the same, because now they're actually used to these objects, they're able to think about it. So before, you basically just come up with a task that's mismatched to the population you're trying to study, and you would make the exact wrong inferences of doing this. So it's an extremely important thing, and it means that if you really want to have meaningful cross-cultural data, you can't just helicopter in and run some task in 2 weeks and leave and think that's the end of it. You need sort of dedicated people there, maybe long-term dedicated field sites where people really understand the local population, where they have good relationships with them. And this is not easy. It's really, really hard for the researchers to do, and it's really, really expensive potentially. It's not something that you can just do as a PhD student, go for a year or something and get the data you need. So it's hard. It's a hard problem.
Yeah, it is. I mean, I've already discussed it with, in fact, Clark Barrett, Joe Henrik, and others on the show. So yeah, it's complicated. So the next question, I think, is an interesting one, because I would guess that many people don't think often about this, but when should psychological scientists test hypotheses? Or to put it in other words, is there some sort of process they should follow before they feel ready to test their hypotheses?
So there's no process in the sense that it doesn't mean there's no answer to the question, but science varies. The way people do science varies in different fields, and even within a field like psychology, for different questions. Where you are in your research program, how much you know about something is going to determine whether you're mostly in sort of doing exploration or really targeted hypothesis tests, or what methods you're using. And so there's no way to prescribe one specific answer to this. Of course, there are some general principles that many scientists, including psychologists, which is where we've been thinking about this the most, could benefit from. And so one of the things is that when you do a hypothesis test, you want it to be informative. So you want it to be that ideally you do this test and you learn as much as possible about the thing you're hoping to learn about. So maybe you're testing two competing theories and you want to know which one accounts for the data the best. Or maybe you're trying to just falsify. You're like, you love Popper and you're like the one psychologist who actually does disconfirmatory research as opposed to confirmatory. Not to bag on psychologists. I think that's like this in every field. So you decided you're really going to try and disconfirm your thing, but then you just make up a scale when you do this. You're trying to measure, I don't know, mood or something, and you make up a scale. And then you don't run a study with that high statistical power, and you don't even know really what this mood construct means. And then you get a result, right? And the problem is that you have this, maybe some hypothesis up here, but then you have to go down this chain. You go down this chain from the hypothesis to the operationalization and the method and the statistical test. And you need to know the concept and all these things. And all the parts of that chain are weak in the sense that you have all this uncertainty in there about, is this really the right way to operationalize it? Is this really the right amount of participants to detect the effect? Whatever. And so at the end, you get some result, but there are so many reasons that you could have gotten a certain result. For instance, you get a negative result, but is that because your measurement instrument was off? Is that because you didn't really understand the construct. Is that because you didn't have proper statistical power? All of these things. And so you need to make sure that your derivation chain, so this chain that leads you from the abstract hypothesis or abstract theory you're testing to all of the things you need to do in order to be able to actually run a study and do a test, you need to make sure that all those things are strong. And I was thinking about this a bit. You know, we have this oftentimes, I think, it used to be, I don't know how evolutionary psychology is now, but there used to be, for example, people were really interested in the concept of genetic quality or something like this, right? But you can't really measure genetic quality. And so you use proxies like maybe facial symmetry
Yes.
or pick your one that you want to use. I don't know, muscle mass or chin chin manliness or whatever. Well, I don't know what people do now. There's many different things that you can do, and then you find some effect, but then you're not, for me, I think, yeah, okay, but I don't really know how that thing relates to genetic quality. You have to really show me that that thing is a really good proxy for this other thing. Otherwise, there's all this uncertainty, and anyone who's skeptical can just write it off, basically.
Mm-hmm.
Um,
Yeah.
so, and that type of thing really slows down scientific progress. It's also like if I try and measure fitness and then instead evolutionary fitness, and instead of measuring something closer to what we mean, let's say like number of offspring or number of grandchildren or something, I measure like, I don't know, how many matings I had or something. Well, that's okay, number of matings, but then you have to assume that translates into something else. Or what if I measure some other thing, like, I don't know. You can think of something even more distant from it that we usually measure with humans because we can't oftentimes actually measure fitness. And so then at the end of the day, we don't really know what the data means for the theory. Yeah. So those types of things are nice to fix if you actually want to do informative tests.
Okay, so we've been focusing for the past few questions on social science and psychological science more specifically, going back to more general questions. What is a scientific model?
So models are something I've worked with a bit in my research, and generally a model of anything, including a model of, let's say, a scientific theory, is an abstract representation of the thing. So you use something that abstracts away from some details, and so is a bit of a simplified version in order to represent something else. So, for example, in that model of publishing that we discussed earlier with the information asymmetries and conflicts of interest, publishing is really complicated and scientists are doing complicated things and all the things that are going on in people's heads, and there's all these different papers. And so if you want to have any sort of understanding of that, you can build a model that gets at these general principles or general kind of aspects of those phenomena that are much simpler than the actual phenomena itself, but that then help you at least be able to think about it. So in our model, for example, we assume there's two types of papers, high quality and low quality. And we assume two types of journals, and you assume scientists can only either submit a journal here or submit a paper here or submit a paper here, right? So of course, in reality, scientists can do all sorts of things. They can burn their papers, they can leave science, whatever. But if you include all of these things, then you end up having an abstract representation that is literally the thing you are trying to understand, and then it's so complicated that you don't understand anything. So scientific models are these abstract representations of some phenomenon that we're interested in that then help us. You can derive predictions from them that help us understand things in a way that's formal. So in a way that's not like, well, anyways, we can discuss the difference between formal and verbal models later, maybe, if we want. Yeah.
Yeah. Yeah, so, but how should we think about the relationship between a scientific model and the real world, or the aspects of reality it's referring to?
So there's this nice saying, I think it's by George Box, the statistician, but I would bet maybe $50 on it, but not $5,000. And it's that all models are wrong, but some models are useful. And so that has to be true. If you have an abstract representation of something, it's not the actual thing, so it's wrong. But the way that we think about the relationship between models in the real world is, at least the way I think about it is, so you can use different models for different purposes to help you to see different aspects of the real world.
Yeah.
So to focus your attention on different things. So you can think of maybe in evolutionary biology. Well, anyways, that's maybe not a great example. But but then you can also think about that some models they are less wrong than other models in the sense that they more closely capture the core features of the way the world actually is. So, for example, as one simple example, you can think about, a geocentric model of our solar system. You have the Earth in the middle and all the planets revolving around, or you can think of a heliocentric model with the sun in the middle. Now, they're both models in the sense they're leaving out many things about how the universe works, our solar system works, and just has a couple orbs orbiting around. But one of those models, the heliocentric model, is less wrong than the other model because it actually has the sun in the middle and planets orbiting around it, and that's the way that the world actually is. And so that then ends up providing us with sort of the assumptions that are made in the model are more closely aligned with the way that the world actually works. And oftentimes that's, all else equal, that's a good feature of a model if your model is not just completely misrepresenting some key aspects about the world.
Mm-hmm. So in my previous question, you were mentioning at a certain point two different kinds of models, right? Verbal models. What was the other?
Formal models.
Yeah. Could you tell us about that?
Yeah. So a simple way of thinking about it is a verbal model is usually what we're talking about all the time whenever we have any idea about anything, just a hypothesis. Maybe it's just something that's in natural language. So maybe I have the idea that, when there's harsh and unpredictable environments, then it's adaptive to engage in impulsive behavior. That's just words. So that's a verbal model. Where the formal model is something that is, you can have many different types of formal models, but usually we're talking about something in mathematics or in computational models in code. You can also have structural models, whatever you want to call them. So when you build a Lego thing or something, that's also a model. So that's the key difference between verbal and formal models. And oftentimes, when ideas or fields are a bit immature, you might start with verbal models. It's totally fine, and you might have an interesting idea, like the impulsivity and harsh environments thing. But then the problem is, does this idea really make sense? Would you put, $10,000 on this idea being right? What exactly do you mean by impulsivity and harshness? Do you mean that the mean level of resources in the environment is really low, or do you mean that the probability of the resources going to zero is really low, or sometimes you get down to a really low level, and so it's really hard to think about all of these things verbally, and then just the logical structure of the argument as well is really hard to tell, like the causal links. Is it actually the case that if environments are like this, then impulsive behavior will evolve, for example? And this is really hard to tell verbally. So you might start out verbally, and then if your idea matures, the way it matures is by formalizing this idea in math or in code, and then you can make things more specific and see, okay, this is what I mean exactly by harshness and unpredictability. This is what I mean by impulsivity. I see in these conditions it evolves, in these it doesn't. I'm using this example as just, I was reading a recent paper by Jesse Fenneman and Willem Frankenhaus. I think it was in Evolutionary Human Behavior, actually, where they modeled exactly this. In I guess developmental psychology, people are really interested in these questions, but there were just verbal models, and people were arguing this, and then they modeled it, and it turns out it's really complicated. That impulsivity involves in some behaviors, environments, and not others. It depends on what you mean by harshness and unpredictability, and you can't really do that without a formal model.
Right. So I have one last question. Throughout our conversation, we've been talking about several issues in science. I mean, some of them are common, I guess, across all science. Others affect more the social sciences, as we talked about. When it comes to solutions or reforms that can apply to that we can apply to science to improve the several aspects, I don't know, like, for example, reliability, publishing, or whatever, do you think that these solutions we might come up with could apply to all science, or that we should try to come up with different approaches to different areas?
That's a great question to end on. I have a hard time of thinking of any solutions that you can just apply broadly to all fields of science, given how different all fields of science are, that would be sort of domain generally good. There might be things that produce good effects on average and are maybe neutral or bad for some fields and great for others. But I think this is the key thing that actually the scientific reformers are coming across now. So in the beginning, with all these replication crises, people started saying, okay, everyone should replicate things more, they should share their data, and they should pre-register. And so it was this very top-down thing. And that's okay as a first start, you identify the problems. But now we're coming to realize that you need sort of this mix, just like in governance systems, where you maybe have a top, it's an entity at the top that has some power over the entities at the bottom, but then you also have local governance that deals specifically with local problems and is able to sort of create local adaptation. I think we need the exact same thing in science. So maybe something to do with preventing fraud or something like this. You could have a very general thing that applies to most fields, but for most of the reforms we're talking about, what we really need is we need to generate these ideas and then create mechanisms at the level of specific lower level things. So in different fields, different subfields, whatever, maybe different countries, that allow those things to adapt to the local circumstances. And so this is going to be the big challenge in the next decades, even for the reforms people have come up with that they're already passionate about. How is it that you then go about making it that people in specific fields accept these reforms? And how is it that you make it so that you're able to tune these reforms to their local needs? It's a big problem. But we can do it. I believe it. Yeah.
Okay, so even with the incentives, perhaps some of them negative, I don't know, in the institution of science and the limited knowledge, of course, we have about how humans operate, you're still optimistic about it?
Well, my two options are either stay optimistic or just, throw everything against the wall and cry and hide under my desk or something. So today I'm optimistic. Maybe if I talk with you in 20 years and we've implemented some of these reforms and without considering any unintended consequences or local adaptation and everything is horrible, then I'll have a reason to be pessimistic. But for now, I'm still optimistic. Yeah.
Okay, great. So, where can people find you and your work on the internet?
Just go to my website. So my name is Leo Tiokhin, Leotiokhin. So leotiokhin.com is the best place. My contact information on there, some social media stuff. I'd be happy to hear people reach out and tell me all the things that I said wrong, or some work of mine that they're interested in, or whatever. So it'd be great to hear what people think.
Okay, great. Thank you so much for taking the time to come on the show. It's been a real pleasure to talk to
Thanks
you.
very much, Ricardo. It was really fun.
Hi guys, thank you for watching this interview until the end. To keep the channel sustainable, I would like to ask you to please visit my Patreon page and to consider making a pledge there, starting at $1. If you could, it would be a great help. Otherwise, and if you like what I'm doing, please share it, leave a like and hit the subscription button. You can also support me on PayPal. This show is brought to you by Enlights, learning and development done differently. Check their website at enlights.com. I would also like to give a huge thank you to my main patrons and PayPal supporters Karen Litska, Anne Blanchett, Peregra Larsen, Lau Guerrero, Francis Ford, Hans Frederick Sunder, Ricardo Vladimiro, Craig Healy, Adam Castle, Olaf Alex, Jonathan Wiesel, Jacob Klinkby, Matthew Whitting, Bernardo Wolf, Tim Hollis, Eric Alenia, John Connors, Paulina Barron, Philip Force Connolly, Jerry Mueller, Herbert Gintis, Rutger Vos, Bo Weingard, Rebecca Newberger Goldstein, Dan Demetrio, Robert Windager, Rui Inácio, Arthur Coe, Zup, Marco Neves, Colin Holbrook, Bernardo Seixas, Pablo Santurbano, Simon Colombo, Jorge Espinha, Phil Kavanagh, Mark Blythe, Roberto Inguanzo, Michael Stormir, Eric Neumann, Samuel Andreev, Tiago Nunes, Bernard Ugni, Alexander Dunbauer, Fergal Cusson, Evan Bodrenko, Al Herzog, Don Ross, Jonathan Librant, Oslam Bullet, Nathan Nguyen, Stanton T, Samuel Correa, Eric Hines, Mark Smith, J.W., João Eira, Tom Hamel, David Sloan Wilson, Yacila Dez Araújo, Eden Solon, Romain Roach, Dmitry Grigoriev, Diego Londonio Correa, Tom Roth, Yannick Punter, Adana Rusmani, Charlotte Bliss, Nicole Barbaro, Adam Hunt, Pavel Ostazewski, Nelek Bach, Catherine and Patrick Tobin, Al Ortiz, Guy Madison, Gary G. Hellman, João Linhares, Lida Cosmidis, Sam Afzal, Adrian Yegi, Nick Golden, Paulo Tolentino, João Barbosa, Jules Price, Edward Hall, Edin Bronner, Franca Bortolotti, Gabriel Pons Cortez, Ursula Litska, Denise Cook, Scott, Jackery Fish, and Tim Duffy. My producers is our web, Jim Frank, Lucas Stafiniak, Ian Gilligan, Luís Caetano, Tom Vanagdam, Curtis Dixon, João Linhares, Benedict Mueller, Vega Guidi, Sardas France, Thomas Trumbull, and Nuno Welder. And my executive producers, Michel Rugieski, Rosie, James Pratt, Matthew Lavender, Sergio Quadriano, and Bogdan Kandivets. Thank you for all.